Hi guys, I'm doing a video just today, just for one of my viewers. I told him I wanted to do a video about the New Zealand grid, and this book is all about it. Let's open it up. Here's the map of New Zealand. Let's look at the page before anything missed out. This is just the grid of how the hydroelectric works, and obviously the water goes in through here and it spins the blades, and the generator's up there. See if I can, there we go, it's much better. You can't really see it too much, bloody light. Here it says it all there, it's spiral casing, and it's just the generator. But what I really wanted to show is this. It's in New Zealand. Here we go. This is where I live around here, the Wellington area. Sorry for the really bad quality. It's just it's not too good for me. Well, obviously up here I'll show you. You guys can familiarize yourselves. Let's put the lamp back there just for now. Bastard. Right. Well, how am I going to do this, guys? Sorry. Hope you guys can see, but there's just a bunch of writing there. But it actually shows, this is the scale in kilometres at the very top. And this is New Zealand electricity transmission lines, power stations and substations. Which says it up there. Well, what it says here, see if I can just, okay, that's much better. What it says there is it's existing hydro power stations and thermal power stations, and that is up here proposed hydro power stations and thermal power stations. This is the smallest line here is 50,000 volt lines, or 50 kV. You have 110 kV lines, 220 kV lines. This is AC, by the way. And down here is 500 volt direct current lines. Just on that, a cable with the dots, and that's 500 volt direct cable underneath the C with the crosses on it. And these other things here say to be disposed of, revised July. Well, this is an old book is at July 1979. Operating at 33,000 volts is the little star there. The double star there is operating at 110,000 volts, and the mini star there again shows operating at 50,000 volts. Right. I'll show you here. This is my area, Wellington. I live down here, and some other subscribers live up in Auckland, which is up the top there. Alright. There's Fighting Bay, which is all the way down there. That is 500, though it's 375 volt DC cable, goes under the sea. Well, not in the it's not completely under the sand, but it's in the sea. That is from the South Island feeding to the north. It's a high voltage transmission line under the sea, goes into Wellington, Oteronga Bay, which is where the sorry any of you guys, I'm not good at pronouncing some Māori names. Oteronga Bay, which is 500,000 volt DC lines, go up to Takapū Road, where I live on the motorway. I can see them from my place where I live. I live up in Porirua. It goes up to the Haywoods, and that is a substation. That substation converts it from direct current to alternating. And also all these other lines here, I guess these lines are just for the outline. But Aotearoa Bay, Takapū Road, Pautahanui. I'm guessing these lines here are either the sea lines or they'd be power lines, but it doesn't seem like any of them. Alright. Okay, 220 volt lines. Right, existing. Well, these are proposed direct current lines from, alright, this is Wellington down here, 3 of them, 3 little substations, another Melling substation, the Upper Hutt substation, the Haywoods, and there's a Gracefield substation as well, just down here, and there's 2 110,000 volt lines coming from the Wellington line down there, going up to the Haywoods, then going up to the Upper Hutt. There's a Central Park power line. There's 110,000 volts, and these ones up here, the dots proposed, going up to 220 kV proposed power lines, and they've probably already been built now because this book was, I think, published in the 80s or early 70s or late 70s, somewhere around there. Let's go up. Paraparaumu is quite far from here. Well, I'll actually show how, because where I live, most of the power is from the big DC cable, and down there is the big DC line. It's 375 volts direct current. Don't want to mess with that, otherwise you'll be literally vaporized. And that's the South Island there. We'll be getting to the South Island on that page soon, but I want to go through this one so you guys all know. Alright, so 220 kV lines from the Haywoods. I'm pretty sure, yes, I'm correct, from the Haywoods. Go up to, they go Paraparaumu and go up to Bunnythorpe. And they enter a substation there. And that's a massive substation there. Get probably around circuits, 5 circuits. And that's going, so this is the Stratford area. Stratford area, New Plymouth, Carrington Street. Oh, okay. Alright. There's 220 kV lines going out, and they go into that substation. They get into 3 220 kV lines that are going out to the, well, what's the square? But these are all substations, that squares, oh that's alright, yeah, that square's just showing what's up here. And up here is the substation. There is a 110 kV line going out to Hauera, and there is 2 110 kV lines going to Opukani. And there's another 2 220 kV lines going to New Plymouth, and probably 2 110 kV lines going to Carrington Street. This is in the Stratford area. And the 3 220 kV lines go up. One gets split off to all these other, these are power stations. Yeah, into mini power stations. I guess they're boosted. And it's more 220 kV lines going up and up and up to the Marsden range up there. Hold on, just go up there with my finger. Marsden, and that is a thermal power station, so I may be wrong, so the power may be travelling back down to that. There's more of the little substations in here, but what I know now is power's travelling from the South Island to the north and going up and getting distributed here, and getting distributed up in the Haywoods, going everywhere else around New Zealand. But this is one of our main supply lines, because if this gets damaged or broken or whatever happens to it, we are all literally stuffed. Well, most of New Zealand is stuffed. Alright, into the South Island one. Here is Manapuri Power Station. It's an existing one. and it is a hydropower station. It goes down, so that's 4 220 kilovolt circuits. One or two of them go to the substation, and then they get distributed to 220 kilovolt circuits going to another power station. Then they go up there into Cromwell, and Cromwell distributes 110 kilovolt lines onto Frankton. Then Frankton does whatever they want with it. More up here. This is the upper Waitaki area, just there. It's the massive substation, Twizzle, how A. It's a power station there. Benmore. This is the one. Benmore. Benmore is really the power station which feeds this light here. Oh crap. This light here is running off Benmore. Benmore power station, hydro, is generating the 500 or 375, or I would say 500 kilovolt line goes up. Methven goes all the way up there, as you can see, the little dotted line. Blenheim's there, but these are all 220 kV lines, all of these. Don't need to worry about those, but what I want to mainly talk about is this little line up here. That's 500,000 volts DC, going up to the tip of the South Island, then being distributed out in Fighting Bays there, as you can see, and the North Island, you can see there, gets into the Haywood stuff. And this is how the New Zealand grid is laid out. Some of it has been updated, because since this is South Island generating stations and transmission lines, and North Island generating stations and transmission lines. And this is New Zealand electricity, transmission lines, power stations and substations. So this is basically, and the scale here of kilometers, here with my two fingers, so from here, from 0 to, let me take a look up here. Hold on a second. 0 to, so that's around 4.4 centimeters. So 44 millimeters, and that would be right there. It would be around, that's 150 kilometers just there. It's quite weird. It's probably wrong. It's showing as north. This little dot here. See that dot up there? It's showing north. That arrow. Right, and also what the other viewer wanted to know is how our transmission is. Oh, sorry, distribution throughout for the neighbourhoods. Right, this is, say this is a power pole. No, actually no, underground would be much better. Right, this is how New Zealand power lines work. This is a delta. I'm right, delta. 11 kV to each phase. Or it could be star, but it's usually delta. It's 11 kV each phase, 11 kV to neutral, or no, phase or line to neutral. On a high voltage line would be 11 kV, and both of them would be 11 kV swapped up. So let's take a look at that. So there's red line. So this is how phases work. There's a red phase that's for the number 1. So that's 1, 2, and 3. First, second, and third phase. Blue is always the third phase. Yellow is second. Red is the first. So that's how our lines get distributed. It's a 3-wire system for high voltage lines. It's all 11,000 volts for residential. But in my video 330, that was a mini transmission line like I showed you in the book before. There was 33 and but it doesn't show 11 kV lines because there's too many. Because literally if you showed 11 kV lines, most of New Zealand would be covered in with the little tiny lines. Anyway, let's go back to the Supply Authority transformer. This is the red line, yellow line and blue line. First, second and third phase, and that's the neutral, black. That's what its color is, black. That's your earth supply. So that's earth. The transformer is earthed, and so is the neutral. So the neutral goes from this 4-wire power line to this Supply Authority transformer. It gets earthed. What else? I'll show you here. There we go. Much better. Right, so just say I win consumer A. I'm on the red phase, going to my house, and I have the neutral, which is black, and I'm also earthed. I have my own earthing rod, so is every house here. This house, like my grandparents you've seen in some other videos, it runs on a 3-phase supply. So this is low voltage lines. 230 phase to neutral is 230 volts, and that's because it's a star connection here. These are all star. 400 phase to phase, so red line to yellow line is 400, yellow to blue is 400 as well. Alternating current, of course. This is blue line to neutral is 230, and I guess you guys can see in the diagram here. So this is a typical distribution system. So consumer D wants all 3 phases, that's up to him. Consumer C, and consumer B and consumer A. So this is how it's distributed, I guess, is consumer A is on red, B is on yellow, consumer C is on blue, and consumer D is on all 3 phases, and probably the next house would probably be back on red, and then yellow and blue, and yellow and blue, and whatever. You can have 2 phases coming into your house. That is absolutely fine. So you'd probably have either red or yellow or blue, or it's alright. I'll read the book, which says up here, the writing. Supply authorities in New Zealand use the same system of low voltage electricity distribution to consumers. This line is 3-phase, 4-wire, multiple earth neutral. You've got to listen to that, multiple earth neutral. Actually, I'll put this up here so you guys can read as well. Got it here. Oh, damn it. There we go, that's 3-phase 4-wire system. Let's get back to this so you guys can read the 3-phase 4-wire system. Figure 6.5 shows diagram it to far out. Sorry, typical 3-phase 4-wire low voltage system distribution to consumers from a supply authority transformer. There are 3 live supply conductors called lines, and these are identified either by a standard color coding red, yellow or blue, or by numbering 1, 2 and 3. The 4th conductor is neutral, which is black, or numbered 0. Just here. There we go, if you guys can read it here. Number 0 considered to be, hold on, number 0 is it not considered to be live because it is connected to earth. So the voltage between any 2 lines, called the line voltage, is 400 volts, and the voltage between any 1 line and the neutral, called the phase voltage, is 230 volts. Note in the electrical trade, blah 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 blah. I don't really want to see that. If you want, you can pause it there, but alrighty. For example, 5 consumers A, B and C homes requiring power from domestic purposes only. These consumers receive a single phase supply at 230 volts. Consumer D is a factory with a heavy load consisting of machinery and lighting that requires three-phase and neutral supply. This, once again, is a typical distribution system. Only some homes receive a two-phase or a three-phase supply, like my grandparents' house. And factories will receive a two-phase or a single-phase supply. Well, that's some of them. Whatever they want, they can upgrade that. It's up to their choice and whatever they want to do with it. With a three-phase 4-wire system, single-phase loads should be connected. Sorry, guys. Single-phase load should be connected in such a way that the present equal loads on each line. Remember that. I'll read it again. With a three-phase 4-wire system, single-phase loads should be connected in such a way that they present equal loads on each line. The system then is working over, ideally, to be balanced and ideal, however, rarely attained in the practice because consumer loads are different and vary at different rates, different times. There we go. Different rates at different times throughout the day, supply authorities try to balance. And that is that is how they do it here in New Zealand. Also, the next page, this is quite a long video, but I have to express this out because a lot of people do not know how the New Zealand system works. If you go to Rodelco, he will tell you as well in some of his videos. So this is your distribution transformer here, and your 3 lines. This is showing a short circuit accident, earth fault there. So this is your switchboard here, neutral bar, and this is your link, earth link. This is your line from the blue phase, and it's the electron going into there to the line. It's your 3 fuses, whatever loads you want, but this load is for some metal casing of a toaster. So something has gone wrong, fault. It is shorting to the metal casing, and the earth wire is taking the load. Also, some of the toaster is still going and going back to the neutral bar, and the power goes. It tries to go through there. It goes through there into the neutral line, and also the power goes through the metal casing into the earth wire through the earth bar there, and the power goes through there through the link. There is a link there, but for some reason it's not showing. Oh no, that's alright. Yep, no, it's fine. It's showing there's an earth bar connected here. Oh, there's an earth wire connected here going to the ground, so that's your ground earth rod, and it goes through there into the neutral, back into there, down into the ground, into the earth, and it'll fault current paths which go to the earth rods of other houses, and these are other consumers' neutral bus bars. So just say if this happened to my place, my neighbour would be receiving some voltage going into the neutral bus bars and back into the neutral line going to the going back to the distribution transformer. And obviously by all that time, that's in seconds, that fuse line would most likely have blown. But you see all the electricity goes through my earth, the house, goes into other people's, and also the distribution transformer has its own earthing stake, and it goes into there as well. Yes, my computer's saying it's running low. There's multiple earth neutral here. Now I'll just plug in my computer for a second, as you guys can take a look at this. Bloody hell. As you can see, this is quite fascinating. I like it. I've had this book for many years. My I found it at my grandparents' house. My grandfather used to be an electrician, like I told you guys, and I didn't use it anymore, so I took it off him. Right, go, plug back in. Hold on, my dog's barking. Right, back to this one. Let's put this back up. Yes, my clock has fallen down. Bloody hell. Yes, my clock is very weird. Right, let's take a look. Here. Yeah, I haven't got very good lighting. Alright, earth neutral. Charger. So, this is just natural light. Earth neutral. The neutral supplies Earth effectively connected to the general mass of the Earth and supply authorities transformer. This is due to a done-tie conductor system to the Earth potential, so the maximum potential of any part of distribution network with respect to its surroundings is the phase voltage 230 volts, which is the value considered safe in New Zealand for equipment directly handled by the consumer. That is voltage between any one of the 3 line or live conductors, and Earth is 230 volts. The Earth neutral also allows current to flow when a fault to Earth occurs. That is, when a line conductor accidentally touches the Earth or Earth metal. With this fault current operates protection equipment, fuses or circuit breakers to disconnect the faulty circuit. Thus, in every electrical installation, metal that may become alive or is purposely and effectively earthed. Earthing is covered in more detail in Chapter 11, and if you want, I'll do another video on earthing and that stuff, but this is how double earth neutral, MEN, means that the neutral conductor is not only the source of the supply, but it also at one or more points along the distribution line in each consumer's premises for the resistance between the point and neutral conductor. Earth, but being required electrical supply regulations 1976. I told you this book is very old, but it's still, the theory is still the same. Not exceeding 10 ohms, but now probably the number has either dropped because of maybe the codes have changed over the years from 1976. I'll tell you now. If you follow that code, I advise you please to stop. In the typical distribution system shown in figure 6.5, for example, the neutral is shown earthed at the transformer and each consumer's premises. The neutral is multiply earthed so that if any live part of the supply system or consumer's distribution systems come into contact with the Earth, the current will flow back into the neutral by the way of several parallel earth connections, and the net resistance of the fault circuit will be low. Even if one or two connections have a high resistance, the lower resistance of the fault circuit or higher the fault current, and the more reliable protection equipment, fuses and circuit breakers. At each consumer's premises, earth continuity or conductors connect the metal that may become live onto an earth bus bar on the switchboard. This bus bar is linked to the main earth connection, like I said before, and earth fault becomes direct short circuit to the neutral, and by the way of the earth continuity conductor, the earth bus bar, the link, and the neutral bus bar. Thus, the fault current does not take a roundabout path that would create a risk of shock or fire in unexpected places, like you touching the toaster. That would not be very good at all. Where were we? This fault. Instead of a heavy fault current flows direct into the neutral bus bar, and blows the fuse or trips the protective circuit breaker on the consumer's switchboard, thereby disconnecting faulty apparatus. Another feature immune system is shown in figure 6.6, where the main neutral conductor accidentally breaks at, say, point X. Now, if the same earth fault occurs in the... I don't know, I have to turn the page. This is just showing electrical shock and what happens. Consumer's apparatus fault indicated by the arrows following back to the transformer. The neutral, though low resistance parts provided by the earth connections of several other consumers in parallel. Thus, the importance of good earthing on every installation cannot be too strongly stressed, and that is very true. Also, Roselka's one of his videos, he did stress about earthing. I told you in this book, because if you don't care about the earth, you may as well just get an electric shock just to feel like it, what happens without an earth. Anyway, earthing is a safety measure required most serious consideration and the highest possible standard of workmanship and maintenance discussed in Chapter 11. That's how, gone a bit far in that, but that's how the New Zealand distribution works, and also yeah, and also how they are earthed and that stuff. So see point X there, this just say if that breaks, what they're saying is when you have your earth rod connected, it goes through your earth rod into the other people's consumer units, back to the distribution transformer, back into the neutral, and then of course in that time, like I said before, it would trip, and like it says here, it would blow the fuse or trip the circuit breaker. So guys, this is has been a long video. If you have any questions in the comments, I hope I covered a lot of the things, but in the comments just ask any questions, I'll be happy to ask them. Some of the questions I may not be able to answer because they may be too difficult, but a lot of the things I will be able to answer, so just drop a comment, and I hope you like this video. So you can't really get these books anymore. I'll probably do another video on electrical shock and how this man has probably survived all three of these, but who cares? Let's see, it's chapter 11. I may you see this is here, just a little extended video just here. Right, this is just how an isolation transformer works. The man there with the drill, and that's also here how to help someone back in 1976, how to treatment for electric shock. Obviously I haven't had to do that, and I don't really want to do that. So chapter 11, just go up to this is about voltage and current. Where's chapter 11? Chapter 8. I'll have to skip quite a bit. Sorry guys, I'm just trying to find chapter 11. This looks like it's earthing here, but this is main series box. But yeah, this is a lot of the stuff in this book is still used today. Oh, who cares? Oh. It is still used today in this protective device. See, this is your fuse here. Circuit breakers. And this is your typical PDL light switches, but quite old. Yeah. Okay. Yes, I'm alright. Yeah. Sorry, it's just my brother. It's just a typical idiot. Just trying to find the oh yeah, here we go for the English viewers. Here we go. In this book, it does have a UK plug, and also it does have a single phase. It shows you here the porcelain insulators here. In the cover, I've got one of these. Mains entry box, and this is how they do it. I've seen a lot of houses how they've wired up, and it looks typically mind my language, but it looks like shit. This is a British plug done properly. 13 amp fuse there, and your fuse cover there. I should do a review about this book sometime and tell you how things work in New Zealand, because see, this is all this stuff here. It still works for ovens, like oven there, plug sockets. It's just if you need to like work on something, absolutely perfect. It's chapter 11 installation methods, but I'm not going to go too far into that. This is typical completion notice, application for wiring permit. I think this is 1976 as well, and it asks you all these questions, like completion notice. Alright, here we go. This is more of the isolation transformers. But yeah, I should do, if you guys want to do a review on all this, I will be happy to do it on all this, because it's quite fascinating for the electricians out there. But this is working area of a kitchen. This is providing plug sockets. This is probably doesn't apply now, but a desirable provision 6 and minimum provision 4. So my grandparents' place was built in 1980 or 1981, and I look at these rules here, and because this book most likely still applied then, and I looked store, workshop, garage, 2 sockets, but there's more. But my grandfather was an electrician earlier on, and he knew how to do this stuff. But right, so you just go a little bit further into this video, just here, just about motors, just flicking through the pages of this book. Just tell me in the comments if you want me to go through this book. It's going to take me a very long time, but it's a 37-minute video, but transformers and that stuff. But I hope you like this book. New Zealand Technical Correspondence Institute. I'm not funded for this, by the way. It's probably a stupid answer, but yeah. So this video was about how the transmission distribution works. But if you got any questions, like I said again, just ask me in the comments, and I'll be happy to answer them for you. So this is the end of the video. So until next time, thank you for watching.